Hello, good evening. It's a continuation of our EASY lecture series. It's May 15th, 2020. It's 7:20 p.m. In Zurich, where I am. It's 10:20 in Davis, California, where Han and Heshan are. Our lecturer tonight is going to be Mr. Heshan Wang. He's going to talk about probabilistic models, linear and nonlinear wave propagation, uncertain wave propagation through material. And then Dr. Han Yang is also with us, and he gave us lectures, and he's going to give us some more lectures on energy and measurements of energy and using energy to control designs and assessment and so on. So with this, we'll give control to Heshan, and what we're going to do is we're going to cut off our videos, our cameras, because there are issues with internet, so we try to minimize the bandwidth. So Heshan, take it over and click on your screen share. And then
Okay.
I'll cut off my camera. I'll stop my video.
Okay.
Can you share your screen?
Yes, I will share my screen.
Okay, let's see how that goes.
Yeah.
And
So
I'll
can
stop
you
my
see my screen?
video. Okay, so I stopped
Okay.
my video. Okay, good.
Okay. Yeah.
Good. Yes, please
Yeah.
go
So
ahead.
today we will today we will continue our talk on uncertainty quantification using Galerkin stochastic finite element method. So in our previous lectures, we already show some theoretical formulation and presentation on how to solve this problem of the uncertainty quantification. Essentially, what we care about is such a uncertain equation of the motions, where we have both the uncertainties on the left-hand side and also the right-hand side. And we already show some techniques to do the uncertainty characterization, essentially how to quantify the uncertainties in the input. We already show the technique of Hermite polynomial chaos Cahulian Loewe expansion to quantify the marginal distribution and the correlation structure of the input uncertainties. And we also presented the method of Galerkin stochastic finite element method to do the uncertainty propagation, essentially to propagate this uncertain forcing to the uncertain random system so that we can get the probabilistic dynamic structure response. And today, we're going to show you two examples. So the first example is we have 8 1D share elements with elements size 100 meters, and we want to considering both the uncertainty in the structure system, which is the stiffness. It can be either elastic or elastoplastic, and also we might want to consider the uncertainties in the ground excitations. And first of all, we're going to characterize the uncertainties in the stiffness. So for the first example, we will consider a linear elastic material with the uncertain shear stiffness G as a random field. And we will consider this random field as a log normal distributed random field with a marginal median 41.7 megapascal. And we consider different amount of the variability in the marginal distribution. Here we are considering sigma equal to 0 0.1, 0 0.3, and 0 0.5. And we use an exponential correlation structure where with the correlation length at 10 elements, essentially 30 meters. And here we give you idea, uh, along with different amount of the marginal variability, how the marginal distribution of this uncertain stiffness looks like.
Okay, can
And
I just
the
Heshan, can I just
yeah,
add
sure.
words here? Can I just add something? So go back. Yeah.
Yeah, sure.
So
Yeah,
it is important for some of these physical fields, physical stiffness fields, physical mechanical fields, to use distributions different than Gaussian, because in this case it's log normal. You cannot
yeah,
have stiffness that goes negative. Now, of course, it's a very, if you use normal distribution, it's going to be a tiny tail that might extend into negative, but it's not a good idea. So in this case, we say, well, it should be something else than normal distribution. So in this case, log normal distribution. So as you can see on this graph, uh,
yeah.
the field is completely, I mean, it's a positive stiffness. That's very physical, and that's the way it should be. Go ahead, please.
Yes, that's true. Yeah. And yeah, that's true. Yeah, so we use a log normal to capture the positive definite nature of the stiffness. And the important thing is that, so now we want to characterize such an uncertain random field. And as I mentioned before, we need to use enough number of the orders and also enough number of the polynomial chaos dimensions. So here we are checking, which order of the polynomial chaos we should use to capture the marginal distribution. As you can see here, so the order one, which is the Gaussian distribution, there is a quite noticeable bias to capture the shape. And once we increase the order from order 1 to order 2, yeah, in this case, it's already very reasonable capture all the marginal PDF. So we can detect, PC order 2 is sufficient for this case. And on the other hand, we also need to determine how many number of the number of how many dimensions of the polynomial chaos we should use. So here we are checking with the different dimensions of PC: dimension 4, dimension 2, dimension 4, and dimension 6. So in this case, we found PC dimension 2, there's still a kind of noticeable difference. So and once we increase the dimension from order 2 to order 4, we have already a very reasonable match to the underlying theoretical uh, exponential correlation. So in this case, we will choose PC dimension 4 as our final choice. So overall, we're going to use a PC of dimension 4 and order 2 to quantify such input uncertain stiffness field.
Can I ask a question? Can I ask a question,
Yeah,
Heshen? So
yeah,
so if you use PC dimension 4 and order 2, do you remember
uh-huh.
how many extra terms you get for each of the degrees of freedom?
Yeah, in
How,
this case, it's just 16 terms,
so,
yeah, in total.
so 16 terms for each DOF.
Yeah, for each DOF,
So
yeah,
that means
essentially
that
the
you
system,
had
yeah,
eight nodes. So 8 times 16, that's 80, 120, 128. So essentially you end up with a system
yeah,
of 128 by 128. Yes. Good.
yes, yeah. So it's not quite large in this case,
Okay.
yeah,
Good.
yeah. And also we need to characterize the input excitation. In this case, we will first considering a deterministic excitation using a simple Ormsby wavelet with a PGA at 1 G, and with a different four corner frequency at f1 0.5 hertz, f2 1 hertz, f3 10 hertz, f4 10.5 hertz. And once we propagate such a wave through the uncertain stiffness field of stiffness uncertain structure system, we can get the probabilistic structure response. So here I'm showing you the, maybe I need to zoom in a little bit.
Yeah, that's a really good
Yeah,
idea. Yes. Yes.
yeah,
Good.
yeah. So here I'm showing you the probabilistic response of the surface node. Here this is a marginal mean and marginal standard deviation of the acceleration of the surface node, and this is a marginal mean and the marginal displacement uh, of the of the of the top node. The one of the quite important observation here we can make is that though all of this all of this stiffness uncertain stiffness field, they have the same the mean value as as in the deterministic case, but you do see the when we increase the uncertainty in the structure system, it will even influence the mean value, especially when you have a very large uncertainty. And this kind of property cannot captured, for example, by some other uncertainty propagation method. For example, uh, uh, like a like a perturbation approach,
Yes.
because in the perturbation approach it only holds for the very small uncertainty, and
Yes.
for that very small uncertainty it will have the same mean response as in the deterministic case.
Can you
But
zoom in?
actually you
I'm
can
sorry,
see,
Heshen, can you zoom in some more on
uh,
that upper left graph? Zoom in all the way. Yeah, and
yeah,
move it to the right so we can see.
yes,
You know, I think you need to grab the bar at the bottom. Zoom in more. Yes. So there you go. So the green one actually undershoots significantly, and that the reason is that it's very uncertain
yeah,
elastic material.
yeah. So sometimes it's also overshoot, yeah,
Yeah, yeah, but
it depends on
it's
where you
quite
look. Yeah,
off. It's quite a bit off.
yeah,
Yes.
quite off. Yeah, it's quite a bit off. Yeah, and there the significant uncertainty depends on how much uncertainty in the output response depends on how much the uncertainty in the input. Yeah,
Okay. Okay. Good. Excellent.
yeah, and now here I'm showing you the response of the response of the surface node. But then now we are showing together the mean value and the mean plus minus 1 sigma. So you can see, if you only do your design based on this deterministic case, well, it might be quite off. Depends on how much uncertainty in the system. For example, in this case, you know, the for example in this peak, is almost 50% than the mean value, right? The plus minus range
Yeah.
of the response. And in some applications where you not only care about plus or minus 1 sigma. You might also care about want to go even close to the tail distribution. For example, here we are showing you the mean and the mean plus minus 1 sigma, 2 sigma, and the 3.719 sigma. So the value of the 3.719 sigma here is corresponding to the probability of the 10 to minus 4,
Okay,
the
I
p-value
think
of 10 to minus
Heshen,
4.
I think we lost internet for a second. I think so. The 3719
Oh,
sigma is 10 to minus 4 probability, and this is showing a
uh,
significant increase. Yes, thank you.
yes, that's true. Yeah, yeah. So yeah, for example, in some risk applications where people do care about this tail distribution,
Yes,
then you need to be able to to have an accurate estimation for such a tail value. Yeah,
yes,
yeah.
great.
And then we show the second case. So we still have the same model, but now we have a different input characterization for the uncertain stiffness and uncertain random excitations. So for the random stiffness for the second model, we're going to use a probabilistic constitutive model, a nonlinear model, which is based on the vanishing elastic region and Armstrong kinematic hardening. And as you can the equation is showing here, and here we have two random two parameters. One is HA, the other is the CR. And here we use the HA as a log normal distributed random field with a median value of 17.4 or 17.6 megapascal. And here we're considering 15% of the coefficient of variance for such a marginal distribution. And again, we use the exponential correlation with a correlation length of 10 elements for such a random field. And we use the same technique as I presented before. So eventually we can determine that for such a log normal random field HA, we need to use a PC dimension 4 and order 2 to quantify that. And in this case, we use the deterministic CR so that we can have a uncertain strength, because the strength is for this model is controlled by HA over CR. So
Yes, go ahead, go ahead.
yes.
No, go ahead. When you're done, give me a word.
Oh, so we use the deterministic CR will give us also an uncertain strength. Yeah.
So the HA is that initial slope, the stiffness, and then HA over CR will be that horizontal asymptote. Can you zoom in
Yeah.
on that graph on the right side?
Yes.
Zoom in so we can see a little more. No,
Yeah.
zoom in more. Zoom in more. Make it big on the screen. Zoom in all the way.
Now
So make it twice as big. Yes, more. So essentially, what you're showing there is
uh,
this is compared. This is essentially a verification with Monte Carlo, and we talked about this
yes.
last time. We said that with Monte Carlo, it's about 1,000 times slower to get this,
Yes.
but this actually shows the plus minus quantiles 30, 70, 10, and 90%. Yes,
Yes, that's true.
excellent. Good. Okay,
Yeah.
thank you. So go to next.
Yeah.
Yeah.
Yeah. So yeah. So this is our probabilistic characterization of the stiffness term. And then we also need to characterize our uncertain input random excitations. So here for a specific site, we can choose a we can figure out what are the possible motions that we can get. In this case, we have been considering, I think, maybe around 500 realizations of the possible motions. And you can see here they have the different peaks and the different time evolving characteristics. And it's very important for us to figure out, so what is the marginal distribution when we considering all these uncertain motions, because we want to propagate all these uncertain motions in a single shot. So here we have done some statistical analysis for the uh, marginal distribution of the motions. And as you can see here, for we this is the frequency density of the accelerations at the 10 seconds and 13 seconds. And we also do the similar check for all the other time steps. We find that both of them can be quite well represented with a Gaussian distribution. So we can assume that not assume, we can verify that. So such a ground motion process can be represented by a Gaussian random process. And also, it's very important to characterize such a Gaussian learning process with Hermite polynomial chaos. So in this case, we have tried different, because it's a Gaussian process, so we only need to use order 1 to represent our ground motions. And we have been using different dimensions like dimension 40, dimension 17, and dimension 115 and 200 dimensions. And by checking that, we found that in this case, PC dimension 115 can already well capture the uncertainties in the ground motions. And and here we can see that we are comparing the statistics from this input ground motion realizations, and also the statistics synthesized from our Hermite polynomial chaos Cahulan Loive expansion. As you can see here, we can not only well capture the marginal distribution of the ground motions, but also the correlation structure of the uncertain motions. So once we characterize both of these uncertain motions and uncertain structure parameters, we can use the stochastic elastoplastic finite element method that we presented in the previous lecture to do the uncertainty propagation. And and from that propagation, we can get the probabilistic dynamic structure response. So here I'm showing you the time evolving mean and the time evolving standard deviation of the response of the top node. And also I'm showing you the mean relative displacement of the top node and the first node relative to the ground, to the ground, to no, not the ground, is related to the to the basis of the model. And as you can see here, because of this is the elastoplastic model, we have some like permanent deformation in the mean of the relative displacement. And very interesting point here, we also observed some uncertainties in the permanent deformation in the standard deviation of the relative displacement. And from the probabilistic dynamic structure response, we can also construct the evolution of the PDF of the displacement for the top node. So, so here I'm showing the PDF evolution along with the time. So initially, because everything is start from the deterministic. So initially, the PDF is going to be a a delta function. So we couldn't show that. So we here we already cut off that, and we start to show the evolution from 2 seconds. So as you can see here, the general trend is that along with the propagation, initially the PDF is very peak, which means the system is very certain, is very deterministic. But along with the propagation of the uncertain motions through the structure, you can see the dispersion of the PDF, which means the uncertain, which means the structure response becomes more uncertain. But towards to the ending of the excitation, because the structure is going to die down, so the system will become peak again. Essentially, the response will become more certain and more deterministic, and towards to the initial state. And and here just to show you the PDF of of 4 different time steps. As you can see here, initially it's a very peaky distribution, and along with the propagation, it becomes a more uncertain with more dispersion, and then it will becomes to uh, show high peaks again. And we can also get the PDF of the PGA at for different node. As you can see here, so the first node has a relatively large uncertainty in terms of the PGA. And with that, I think that's all we want to
Good.
say today.
So
Yeah.
one thing, if I can add, so essentially
Hmm.
the response has a full probability density function of all the components of displacements, velocities, accelerations,
Yeah.
stress and strain, and then you can pick up whatever you want to look at. In
Yes.
this case, you showed PDFs. What you can also do, you can integrate that, get CDFs, get fragilities, and this is all by taking essentially complete uncertain information about the excitation function. In this case, some motion at the bottom.
Yeah.
Next time we'll talk about that some more, because with this method you don't really need to pick up intensity measures because you have a complete information.
Yes. That's true.
Well, so why don't you stop sharing
Okay.
the screen and I'll turn our videos on. Han, can you turn your video on?
Yep.
Um, well, okay, so thank you very much. So we'll stop here. We'll continue next week probably. with some more subjects on probabilistic modeling. Now, taking into account real earthquakes and doing realistic probabilistic seismic hazard analysis with this type of propagation. And then we will also look some more into some interesting and exciting energy propagation calculations, some fairly new developments. So with that, stay healthy, wash your hands, and I'll talk to you soon. Bye.
Yeah, bye.